Okay, let's talk about electrolysis, and this is difficult. I'm not saying it isn't, but if we use skills we already have, we should be able to do these fairly reliably. We have to have a clear plan, and we have to be very organized. Units will be more important than ever. So you need to make sure in your one-page summary or your one-page wonder, you have your units written out so that you can use that when you're trying to solve one of these problems. And I suggest you get that done before you attempt these problems. So let's go. What is an electrolytic cell? So far, we've been talking about galvanic cells, cells that will supply us with energy. In other words, a battery. This, however, is the reverse, where we are putting energy into the system so that we can get a desired output. In this case, we usually are plating metal onto a surface. So it is a non-spontaneous cell. Delta G is positive. Energy is supplied from some kind of a power supply, and that pushes a reaction forward. And like I said, it's used to plate metal onto a surface, like silver plating a spoon or something like that, or base metal. They are very similar to voltaic or galvanic cells. We still have our anode and our cathode, and those reactions are still the same. Oxidation is still happening at the anode, reduction is still happening at the cathode. Instead of having the cell supply the voltage, we are supplying the voltage. And then the cell potential, since we're going in the reverse reaction, E naught will be negative, and we still have a salt bridge. So the few things that are different is where the energy is coming from and going to, and therefore what E naught is. So here is a link to a demo I did with you guys very early on in the year when we covered reaction types. This isn't my video, but it shows you the decomposition of water or the electrolysis of water. And I think you should watch that. So you could pause the video here and write that down. Unfortunately, you can't click on it, and I'm not going to click on it now. But it's one that you can watch, or you could go and search YouTube for it. So I also want you to read in detail some everyday chemistry in everyday life. And it's talking about electroplating. This is in your book, and I think that you'll find it very interesting, and it'll help for you to see what's going on and make it a little more, real. So, calculations. We're going to use this equation only, and we need to know what those values are. So, I is the current in amps, and that is this first letter here. It doesn't really look like an I, but it is. This letter is T, which is time in seconds. N is the number of moles of electrons that are being transferred. And F is Faraday's constant. So you'll definitely need that written down on your one-page summary of this chapter. You can be asked to either calculate the time it will take to deposit a certain amount of metal, or you can be asked how much mass will be deposited in a certain amount of time. And so you'll have to go through these calculations to do it. The next two videos, I'm going to show you what the book talks about, but then I'm going to do two additional videos, one for doing a time problem, one for doing a mass problem, where I do it the way I think of it. And I use dimensional analysis. What they're doing is smaller calculations that they then continue on with, which I don't care for. I much prefer to set up one long calculation, check all my units, make sure I'm coming out where I want to come out, and then calculate. But as I said, either way is perfectly fine. So if I want to this problem is asking me how much metal will be deposited. So in the process used for electroplating silver, a current of 10.23 amps was passed through an electrolytic cell for exactly 1 hour. And remember I said time had to be in seconds. And then I asked how many moles of electrons passed through the cell and what mass of silver was deposited on the cathode from a silver nitrate solution. So in this case, I would, if you do it their way and you give me the two answers, that's fine. If you do it my way and you've set it all up, you would get credit for both parts, even though you only did one calculation. So we know that Faraday's constant is going to be used to convert the charge, or Q, into moles of electrons. So they're doing that calculation first, figuring out how many moles of electrons are being transferred. So to do that, and so let's go back up to our equation. So they're going to take this equation and they're using the Q part with the N times F. And they're going to then rearrange it to have Q divided by F gives us the number of moles. So Q is coulombs per second, or an amp, times the time. And here they're converting that time into from hours to minutes, minutes to seconds. And then they divide by Faraday's constant, which then gives us, and they did one calculation on top and left the calculation on the bottom, which I think is stupid, and got to this many moles of electrons. So then they take that answer, or they then are looking at their equation, and silver metal is deposited by reduction, gain of electrons, yep. And one electron is involved in that transfer. And so then they would take now we're going to go back to this equation. Oh, no, we don't need this one. So we're going to take the mass, and we have moles of electrons, and 1 mole of electrons for 1 mole of silver, which is where they're getting it from right here, these two things, a mole-to-mole ratio. And then this is the molar mass, and they get how many grams would be deposited. So that's pretty straightforward. I think I do it a little bit more easily. So we'll talk about, and I'll do this exact question again in another video. So here's the second one. What is the time? So this is time required for deposition. In one application, a 0.010 millimeter layer of chromium must be deposited on a part with a total surface area of 3.3 meters squared from a solution containing chromium-3 ions. How long would it take to deposit a layer of chromium if the current was 33.46 amps and the density of chromium metal is 7.19 grams per cubic centimeter? So we're going to have to go back and do lots of conversions here. If the total charge can be determined, and then the charge can be obtained from the amount of chromium needed for stoichiometry, so you're still going to need a balanced equation, and that would be one of your half reactions. The amount of chromium can be obtained using the density and the volume required for the thickness of the area, the thickness times the area. So volume is going to be the thickness, and that has to be converted to centimeters. And then we have we already have the total surface area. So thickness times area gives us the total volume, 33 centimeters cubed. Now that we have the volume and we know the density times volume would give me mass. So they do that small calculation and get that this is how many grams they want. So once they get that, they take the grams of chromium divided by the molar mass to get the moles of chromium that will be deposited. Then they take the moles of chromium, and they have to, and they didn't really write out their equation, but they should have. For every 1 mole of chromium metal, it will require 3 electrons. And for every mole of electrons, it's 96,485 coulombs, and that will give you the charge. We're still not done. You can see why I don't like these little calculations, I think, at this point. Now they're going back and using the equation that Q equals time times the times I, the current. And so time would equal the coulombs divided by the current. So the current is way back up here in the problem that it's 36.46 amps. So the coulombs divided by the amps is going to give us how many seconds. And then it doesn't tell you up here how to convert that. You could leave it as seconds or you could convert it into hours. Either one would be fine. So this one I think is particularly fragmented and difficult to follow just because of doing it in so many different little calculations. Anyway, so I'm going to go through and do these two problems again, but do my method so that you can use either one. You'll have two examples of it. Thanks for listening. Bye.